The last case of symmetry for Gauss's law, we have done spherical and cylindrical so far, is planar symmetry. Planar symmetry only obtains for one or two cases, so this is a pretty restricted case, and you can think of Gauss's law as applicable to something like a sheet of paper. If you're really close to this sheet of paper, well, you can think of it as an infinite sheet. So that's our workaround, because we'll be pretty soon applying this result to something like a capacitor, and capacitors are really small, about the size of your fingernail, and we are still going to think of them as infinite sheets. So that's one of the great mysteries of the subject, that you can apply it even when the infinite approximation is awful. So let's take the idealized case of an infinite sheet where I don't indicate the corners, so it looks like infinite sheet to me, and the charge density is sigma naught. This is an areal charge density, which means its units are coulombs per square meter. What type of Gaussian surface will you use to address this? This is a famous Gaussian surface for this example, and it's called a pillbox. I have to emphasize the shape of the pillbox is not important. It just needs to be prismatic. In other words, whatever shape you give it, it needs to be the same above and below. So I could make it look like a broccoli stalk if I wanted to. It's harder to draw, so I just made it look like a cylinder. And I'll call this area of the cross-sectional area of the pillbox simply A. So the charge enclosed by the pillbox is simply A times sigma naught. Because sigma naught is coulombs per square meter, that times square meter will give me coulombs. So the right hand side of Gauss's law is very simple. Let me just write that right away. Q enclosed is equal to sigma naught times A. The left hand side of Gauss's law, what is that? Well, if you have an infinite sheet of charge, let's say it's positive charge for the sake of drawing something, then it's going to put out electric field above and below. So electric field is certainly going to go out like that, go out like this, and from the sides it's going to go out like that. Now we don't know how big it's going to be, so let's just maybe draw it a little bit bigger on the sides, because we don't know how it's going to look. It's certainly not going to have any components in this direction because of the infinite symmetry. So that's what we have. What about the area vectors? On the top surface, you're going to have dAt. The area vector on the bottom surface is dAb, and the area vector on the curved surface is dAc. I'll put one here also. Gauss's law is a law of nature that says that the enclosed flux due to the surface known as the Gaussian surface S, and that enclosed flux is the oriented double integral of the electric field dotted with the area vector everywhere on that imaginary Gaussian surface, that is called the electric flux phi E on the closed surface, is equal to the enclosed charge divided by the constant of nature called epsilon naught. The right hand side, as I have mentioned, is already known. The left hand side needs to be worked out. So the left hand side is going to be like this. I'm going to break it up into three parts, just like I did in the previous video, because the cylindrical Gaussian surface, the technical name for this is a prismatic pillbox. The top surface, E dot dA top, plus the curved surface, E dot dA curved, plus the bottom surface, which is E dot dAb. The curved surface does not make a contribution because of the 90-degree angle between the electric field and the area vector. You can see that here as well as here. So I'll put a 0 through the dot product to indicate that it's because of the dot product being 0 that it does not contribute. What about here? The electric field and the area vectors are parallel to each other, so you're going to get a cosine theta factor of 0. Cosine 0 equals 1, and here also cosine 0 equals 1. So let's simplify those two terms. E times dA top cosine 0 degrees plus integral bottom E times dAB times cosine 0 degrees. Now the electric field can only possibly depend on the z coordinate and not on the x and the y coordinates. Alright, so you can only have the electric field depending on z. So I'll write the electric field as a function of z and pull it outside. Now the integral over the top surface of the area is just the area A. So I've done that integral, plus E of z times A for the bottom surface too. So I'm going to get 2 times E of z times A. Now let's use Gauss's law. Gauss's law says that the flux integral must equal enclosed charge over epsilon naught. The flux integral on the left side is 2 E of z times A, and on the right hand side I have the enclosed charge, which is already given by sigma naught times A divided by epsilon naught. So the A cancels out, which it should, because it's a figment of your imagination. So I get the electric field as a function of z is not even a function of z, it's a constant, and that constant value is sigma naught over 2 epsilon naught. A very, very famous result is this: the electric field of an infinite sheet is a constant. It does not change no matter how far you go away from the sheet. That result is actually very mind-boggling, so let's focus on that for a couple of minutes and see why that should be true. So basically what it's telling you is something very interesting. If you have something like the surface of the sun, if you know anything about the solar system, you know that the sun's surface is very big. Okay, the sun's radius is about 100 times that of the Earth's radius, so it's about 1 million miles in diameter. So if you're 1,000 miles from the sun, highly not recommended, but if you're 1,000 miles from the sun or 1 mile from the sun, you are going to get burned up the same. Okay, that's what this is telling us, because if the sun is considered as an infinite sheet of, okay, not charge, but some other object like radiation, radiation goes as 1 over r squared, just like electric fields. So you can use this for light also, or sun's radiation as well. It tells you it doesn't really matter if your eyeball is right against the sun, or if you're 10 meters from the sun, or you're 100 meters from the sun, or 100 kilometers from the sun, or even 1,000 kilometers from the sun, you'll instantly burn up. Well, if you're really far from the sun, like you're where the Earth is, for example, then it no longer looks like a infinite sheet, and then something else has to be used. Sun starts looking like a sphere. In fact, the sun and the moon are about the same size from where we are located. So you cannot no longer use that argument. But very close to the sun, it really doesn't matter how far you are from the sun. If the sun looks like an infinite plane, you're going to get the same amount of intensity here as here. And why is that? Let's take a 45-degree cone. Okay, suppose you have a 45-degree cone. Then you're going to see just this part of the sun, and whatever intensity it's got is going to be at this very close distance. So you're going to get a lot of intensity, but from the 45-degree angle, so it's not much. But if you go far away from the sun, that same 45-degree cone is going to catch, granted at a bigger distance, so each portion won't be as intense, but it's going to catch that much more in area. So the amount of loss of intensity, because intensity falls off as 1 over r squared, is exactly compensated for by the growth in area, because growth in area is also proportional to r squared. So the 1 over r squared and the r squared factors cancel out, and so you end up with the intensity being constant. So that's the reasoning behind why the electric field is constant with distance. So having gone through that argument, let's now focus on what other problems can be solved using this infinite symmetry in 2 dimensions. And the answer is, the one other problem that you can do with Gauss's law is a slab. So suppose I have a slab that's infinite, which I will indicate by omitting out the corners. What type of electric field will I get? So just for the sake of simplicity, I'm going to take a constant density slab. And you're going to have the Gaussian surface pillbox. Now you're going to have two of those, one inside and one outside. So I'm going to draw the pillboxes as just squares for the sake of simplicity, right? And the one outside will look like this. So I'm going to draw a square pillbox, cuboidal. It's a technical term for the pillboxes I'm drawing. So the inside pillbox looks like this, and the outside pillbox is a bigger version of the inside pillbox. The electric field structure is going to be exactly the same as that, so I won't draw it. You're going to get 2 up, 2 down, 2 up, 2 down, and then the sides are all going to be perpendicular to each other. So I won't draw that, and the left-hand side will be exactly the same for all problems with planar symmetry. I'll just focus on the right-hand side. Now I've told you that this is equal to a constant density rho naught. That is, by the way, not the most general. You can also have rho as a function of z, but with symmetry. In other words, it's a function of z in the same way above as it is below. So I put rho as a function of mod z, or absolute value of z. So for example, a possible function of rho could be something like rho naught times 1 minus z squared over t squared, where t is the thickness of the slab. So that's a possible, t is half the thickness of the slab, which means 2t is the thickness. So that's the possible kind of density you can have. But let me just take the density to be constant, because I just want to finish up this example in a couple minutes. So I just want to find the charge enclosed in these two pillboxes, S1 and S2, and let's take the half thickness to be t, which means the total thickness is 2t. The charge enclosed in the Gaussian surface S1 is the volume of the Gaussian surface S1. So the generic Gaussian surface has got height z above and height z below. So the height is 2z. Let's call the area of cross section A. So that's going to be rho naught times the volume, which is the height 2z times the area A. Okay, for S2, the enclosed charge on the larger cuboidal pillbox is going to be saturated when you reach the surface of the slab. So you won't go beyond the surface of the slab. There's just empty space there. So that's going to be 2 times T times A. Done. Let us find the electric field everywhere by using Gauss' law. Gauss' law says the left-hand side, which is 2E times A, must, this is for Gaussian surface S1, must equal the charge enclosed, which is rho naught times 2Z times A divided by epsilon naught. The A's cancel out, one factor of 2 cancels out, and I get the electric field is proportional to just Z. For the Gaussian surface S2, I'm going to get 2EA equals some constant value here, which is rho naught times 2T times A. Once again, the A's cancel out and the 2's cancel out. And here the electric field is a constant. So outside the slab, you cannot tell it apart from an infinite sheet. It looks just like that, constant electric field profile of an infinite sheet. The last step, as always, is to plot this, the absolute value of z as a function of the absolute value of z, which means it's going to be the same above or below. So I'm just going to look at one of them. Let's see what we get. Within the slab, you're going to have a linear profile. Outside the slab, it's going to go off as a constant, just as it did for an infinite sheet.